about functions and welcome to all students. In this lecture, we will learn about functions and graphs of some standard functions. Here, we will discuss about some points. First is definition of function. Second is types of functions. Next is some standard functions, graphs of some standard functions, and a website to draw graphs of functions. See the outline of our lecture. First we will discuss definition of function, types of function, and then finally graphs of some standard functions. So see the definition of function. Function from set A to set B is a rule which assigns every element of set A to unique element of set B. Generally, function f from set A to set B is denoted by notation f from A to B. Now, domain and codomain of a function. If f from A to B is a function, then the set A is called the domain of function f, the set B is called the codomain of function f, and if x is a member of domain A, then f of x is a member of codomain B. F of x is called the image of x, and the function f or f of x is called value of function f at point x. X is called preimage of x. If f from set A to B is a function, then the set of all images in set B under the function f is called the range of function f. Now, range of function f, it is nothing but it is the set of all images in set B, or we can say it is the set of all f of x belongs to B such that x belongs to A. Range of function f is also known as image set of function f. Range of f is equal to image of f, and range of function f is always a subset of B. Now, we see the definition of injective function. A function f from set A to B is said to be an injective function if every image in codomain B has unique preimage in domain A. That is, whenever f of x1 is equal to f of x2, then x1 is equal to x2. Or in other words, we can say whenever two images are same, their preimages are also same. Or we can say whenever two images are not same, their preimages are also not same. Injective function is also known as one-to-one function or univalent function. Surjective function. A function f from set A to B is said to be surjective function if every element in codomain B has at least one preimage in domain A. Or in other words, we can define a surjective function like this. A function f from set A to set B is said to be surjective function if for any y belongs to B, there exists at least one x belongs to A such that y equal to f of x. If f from set A to B is a surjective function, then image of f is equal to B. Surjective function is also known as onto function. Bijective function. Now, a function f from set A to B is said to be bijective function if it is both injective function and surjective function. Now see the composition of two functions. If f from A to B and g from B to C are two functions, then the composition or the composite function of two functions f and g is denoted by g composite f, and it is a function from set A to set C such that g composite f of x is equal to g of f of x for all x belongs to A. For example, Consider a function f from set close the interval 1 comma 2 to close the interval minus 1 comma 1, and function g from minus close the interval minus 1 to 1 to close the interval 0 comma 1 with two functions given by f of x equal to sin x and g of x equal to x square respectively, then composite function of function f and g is g composite f, and it is a function from set closed interval 0, 1 comma 2 to closed interval 0 comma 1, and it is given by g composite f of x equal to g of f of x equal to g of sin x equal to sin square x for all x belongs to closed interval 1 comma 2. Now see the definition of inverse function. A function, or let f from set a to b be a function. A function g from b to a is said to be an inverse of function f if g composite f of x equal to x for all x belongs to a, and f composite g of y equal to y for all y belongs to b. Function is called as an inverse of function g is called an inverse of function f, that is g is f inverse. Function is said to be an invertible function if it has an inverse function. Okay, real valued function. A function f is said to be a real valued function if its range set is subset of the set of real numbers. That is, here if f from a to b is a real valued function, then its range set, a range of function f, is a subset of set of real numbers. Now see some standard functions. So first function is mod function, mod x, or it is also known as absolute value function, and it is defined for all real numbers. Second is exponential function, and it is also defined for all real numbers. Next is logarithmic function. It is also defined for all. It is defined for only positive real numbers. See here. And next function is a quadratic polynomial function. Ax squared plus bx plus c. It is defined for all real numbers. Next is inverse function 1 upon x. It is defined for all real numbers except 0. X raised to n, it is known as power function, and it is defined for all real numbers. Next is sin x function. It is defined for all real numbers. Cos x function is also defined for all real numbers. Tan x function is also defined for all real numbers. So these functions are under the trigonometric functions. So next is sin 1 by x function. For all x belongs, it is defined for all real numbers except 0. Next function is x square into sin 1 by x. For all x belongs to minus infinity to infinity, means it is defined to all real numbers. Next function is x into sin 1 by x. It is also defined for all real numbers. So these are the functions which are included uh, in uh, in this lecture. Okay, and we see the graph of these functions. So let us take first function y equal to mod x, and this is the graph of function y equal to mod x. As we have seen, it is defined for all real numbers. We have taken part of a whole graph. So its domain is minus 4 to 4, closed interval minus 4 to 4, and range is here. Range of this function is from uh, closed interval 0 to infinity. This is the range of that function. It is a positive function. Okay, so function has only positive values. Okay, so as function mod x is absolute value function, okay, it gives positive value for any input of x. Okay, so see here, from if we see, so this function is divided into two parts. So on the see here, the see here on the right side of the y-axis we have one part of that graph, and on the left side of y-axis we have another part of that graph. So on the right hand side of y-axis we see that the graph is increasing as values of x goes on increasing. The values of a function f of x also goes on increasing. And see on the right hand side, so on the right hand side of y-axis the graph of function is increasing graph. So now similarly we talk about the graph of a function which is located at the left hand side of y-axis. In the left hand side, as the values of function increases, the graph, the values of function, as the values of x increases, the values of function goes on decreasing. So in this part the graph of function is decreasing graph. Okay, and at x equal to 0 the function has value 0. So this is our mod x function and its graph. Okay, now next see uh, exponential function e raised to the power x. So see the graph of that function. If we observe the graph of this function, we will see that going from left to right, as values of x goes on increasing, the values of function e raised to the power x goes on increasing. So we say that this graph is function is increasing function. Okay, so if we say the limiting position at limiting position of that function when x tends to infinity is infinity. Okay, and when x becomes smaller and smaller, the values of function approaches to the line. So what is that line? This line is y equal to 0. So approaches to the line y equal to 0 means as values of x goes on decreasing, the values of function approaches to 0. Okay, so this is the limiting position of that function e raised to the power x. So we can say that limit of e raised to the power x is 0 as x tends to minus infinity, means as when x becomes smaller and smaller, values of e raised to the power x approaches to 0. So this is about the graph of function e raised to the power x. Now next we see the graph of function e raised to the power minus x. Okay, so e raised to the power minus x is exactly opposite to the function e raised to the power x. Okay, so see the graph is also exactly opposite. So as values of x goes on increasing, the values of function f of x goes on decreasing, and they approaches to 0. Okay, they approaches to the line y equal to 0. So as x tends to plus infinity, values of function approaching to 0. So we can say that the limiting position or limit of e raised to the power minus x is 0 as x approaches to plus infinity, means as x approaches to or we can say as x becomes larger and larger, e raised to the power minus x approaches to the value 0. Okay, so this is decreasing graph. Now consider the next graph of log x. So as we have seen, the log x function is defined only for positive real numbers. Therefore, the graph of that function is lies. Graph of function log x is located or is situated in first quadrant and fourth quadrant only. So see here we observe that as values of x goes on increasing, the values of function also goes on increasing. In this case, we say that whenever x becomes larger and larger, log x values of log x also becomes larger and larger. Means so in terms of limit, we say that when the limit of log x is infinity as x approaches to infinity. Okay. Similarly, we see on this side of that graph, when x becomes smaller and smaller, when x approaches to 0, the values of function approaching to minus infinity, approaches to minus infinity. Okay, so in other word we say the limit of function log x, the limit of log x is minus infinity as x approaches to 0. This is the graph of function log x. Now next we see the graph of function y equal to x square. So this is also a positive function, that's why uh, its graph lies above the x-axis. Okay, so see here this graph also has two parts. First part is in first quadrant and second part is in second quadrant. So in first quadrant we see that as values of x goes on increasing, the functional values are also goes on increasing. Therefore in first quadrant graph is increasing graph, and in second quadrant as values of x goes on increasing, the values of function goes on decreasing. In second quadrant function is decreasing function, and at x is equal to 0, the value of function is 0. Okay, so this is as x square is a function, as y equal to x square is uh, even function, therefore this graph is symmetric about y-axis. See here, it is symmetric about y-axis. No doubt it is a very simple function. We call it is a square function. Okay, we call it is square function. Okay, so next function is inverse function 1 by x. So this function, as we have seen, this function is defined for all real numbers except x equal to 0, because that function is not defined at x equal to 0. Means 1 upon 0 is not defined, that's why it is not defined at x is equal to 0. Okay, so this function has two parts. First part is in first quadrant and second part of that graph is in third quadrant. In first quadrant we see that graph as x goes on increasing, as values of x goes on increasing, the values of function goes on decreasing. So this is decreasing function. And in third quadrant see also, as values of x goes on increasing, the functional value goes on decreasing. So here also it is a decreasing function. But the so see here, as we have as it is not defined at x is equal to 0, means this graph is broken at x is equal to 0. That's why this graph is not continuous at x is equal to 0. That also we can conclude here. Okay, so in case we see the limiting position of that function, as x tends to infinity, means as x becomes larger and larger, function 1 upon x becomes smaller and smaller, means it approaches to 0. So in terms of limit we can say that limiting position of 1 upon x is 0 as x tends to infinity. Okay, and here also, or we can say so see here, as x approaches to 0, values of functions becomes larger and larger. Okay, so in other word we can say that limiting position of function 1 upon x is infinity as x approaches to 0, or as x tends to 0. Okay, so similarly we can say here, so at this part we can say that as x becomes smaller and smaller, as x tends to minus infinity, the values of function approaches to 0. So limiting position or limit of 1 upon x is 0 as x tends to minus infinity, and the limit of, at this point we can say that as x tends to 0, from the left hand side of 0, uh, function function approaches to minus infinity. So this is all these things. So now consider the next graph. Next graph is a graph of sin x functions. As all of you know that sin x function is the graph of sin x function look like a wave. Okay, so see here, sin x function, we know that the amplitude of the graph of a sine function is the amount by which it varies above and below the x-axis. Okay, so you see amplitude. In this case, the amplitude is 1. And what about the period? The period of sinus function is the length of shortest interval on the x-axis over which the graph repeats. So see here, in this case, the period of sinus function is 2 pi. Here, sine function has a range from -1 to 1. Looking at this sine curve, you can see it never goes outside of this range, -1 to 1. The sine function is an odd function. It is a odd. Okay, it is an odd function. Now we see the next function is a cos function. So cos function is also a, a wave function, or its graph look like a wave. As we have seen, the amplitude of the graph of cos function is the amount by which it varies above and below the x-axis, and the period of cos function is the length of the shortest interval on the x-axis over which the graph repeats. And in this case, here amplitude is 1 and period is also 2 pi. Cos function has a range from -1 to -1 to +1. Looking at this cos curve, you can see it never goes outside of this range. Okay, and cos function is a even function, so that's why we see that it is symmetric about y-axis. Okay, now consider the next function. It is a tangent function. So we see that the tangent function has a completely different shape. It goes between negative and positive infinity, crossing through 0, and at every pi radian as shown on this plot. The period of tan function is pi. As you can see, the tan function has a period pi radian, with each period separated by a vertical asymptote. The concept of amplitude does not really apply here. Okay, so all this about the tan function, and now we will see one function f of x equal to sine 1 by x, and it is defined for all x which are not equal to 0. It is defined for all x but x not equal to 0. The value of f of 0 is not defined. We can see here. For every x not equal to 0, f of x lies between -1 and 1. The function is odd function because f of minus x equal to minus of f of x, and its graph is symmetric with respect to origin 0, 0. Now see the graph of function y equal to sine 1 by x. So you will observe that in this graph, as x goes away from 0, the frequency of oscillation becomes smaller, and as x approaches to 0, the frequency of oscillation becomes larger. Okay, but this function is not defined at x equal to 0, therefore this graph is broken, or this graph is not continuous at x is equal to 0. Okay, so now see the next function is y equal to x square into sine 1 by x. So here also we see that the graph of that function, graph of function y equal to x square into sine 1 by x is a oscillatory graph, but the oscillations becomes larger when x goes away from 0, and oscillations become smaller, and frequency of oscillations becomes larger when x approaches to 0, and it is defined at x equal to 0, and this graph is continuous at x is equal to 0. Now see the graph of y equal to square root of x, positive square root of x. Okay, if we take normally square root of x, so it has two values, therefore it will not become a function. And if we say the only positive square root of x, then it becomes a function. And the graph of that function is like this. So as x, it is defined for only it is defined for positive real numbers and 0. Okay, so graph of that function lies in first quadrant. As x becomes larger and larger, the values of function becomes larger and larger. Okay, so if we in case in other word, if we say limit of square root of x as x tends to infinity is infinity. Okay, so this is the graph of square root of x. Now see the graph of function y equal to x into sine 1 by x. So this graph is also oscillatory graph, and we see that when we go away from origin, the frequency of oscillation becomes smaller, and as we go uh, towards origin, the frequency of oscillation becomes larger. We will see afterwards the graph of this function. Okay, so you can observe here also. So graph is the graph of that function lies between +1 and -1. Okay, now finally we see the following URL gives graph of all types of functions very nicely. If we go to the internet, if we click on this website and go to the internet, we can open the web page where we can plot all types of graphs, and we will take one demo here, interface of this website, and this web page, and just see here. So see here, this is first number, and that here we have to add the function. Okay, here we have to add function. So first of all, we draw the graph of let us our first function was a mod x, and see here the graph of mod x function. Okay, and just enter. So this becomes a graph of mod x function as we have observed, and here are plus and minus sign. If we press this plus sign, it will be zoom in, and if we press minus sign, it will be zoom out. And look at the graph that we have drawn. Okay, secondly we will draw the graph of suppose sin x function, sine of x. So sine of x function is a uh, sine function is a wave function, and we will see the graph of that function. So where is that? Just we have to zoom in. Okay, not zoom in, I think. What happening? Okay, so see here. Okay, see the graph. Okay, so what we have done is zoom in. Okay, just do zoom in, and you will observe this graph. Okay, okay, so this is the graph of sin x function. After that we draw the graph of cos x function, so this is the graph of cos function. Then we draw the graph of tan function, tan of x. Okay, so this is the graph of tan function that we have seen. Okay, then so whatever you will add here, it will give you a graph of that function. Okay, so let us type one function a into sine of bx plus c. Okay, so here we have added here parameters a b c. They are parameters, and if we change these parameters, and then see what will be the graph. Okay, so okay, so we can move this graph here and there, no problem. Okay, so now what we have to do is, if I put a equal to 1, a means amplitude, amplitude is equal to 1. See here, this is the amplitude. Okay, and amplitude means the oscillation of graph uh, goes
The amplitude of the graph of sine function is the amount by which it varies above and below the x-axis. So above of the x-axis it goes to the plus 1, and below the x-axis it goes to the minus 1. So in this case the amplitude is 1. So if we change the amplitude, then see what will happen. So see here, I take amplitude equal to 2. So above the x-axis it goes to plus 2, and below the x-axis it goes up to minus 2. So in this case the amplitude is 2. Okay, so this is amplitude, and I want to make a simple sine function whose amplitude is 1, whose what is this is period is again 1, and then shifting. C means shift of that graph. So it is shifted. See here, it is shifted somewhere. So if I take it in 0, then it becomes our normal sine graph. Okay, it is our normal sine graph. Okay, so this is so by changing the parameters we can uh, look towards the graph in different angles. Okay, so all over this we can now you put your function and draw the graph of your function. So you try this, it is very nice. And now, so let us, okay, let us stop now, stop this lecture. Thank you very much for paying attention here.